And the next speaker is Adi Shamir. He made many very important contributions to the science of cryptography. I'll just mention the famous RSA public key algorithm. Shamir is letter S in this acronym. He was awarded Turing Award in 2002, Israel Prize in 2008, and many other accolades, but I don't want to waste time. And without further ado, Adi, please.
Good morning. I'm working mostly on the interface between security and all other branches of computer science. So today I'm going to talk about the interface between security and machine learning. And I don't have to tell you about the fact that machine learning is undergoing a revolution. It has major achievements in the last few years, but it also has a dark side, and this is that it is incredibly easy to fool. And what I'm going to tell you today is a few research projects that I was involved in, which try to understand why is it so easy to take deep neural networks, which under normal circumstances work with tremendous accuracy, and make them make full decisions. So for those of you who haven't seen what a deep neural network is, you have on the left an input layer. Each one of those points is accepting a real number. If it's an image, it's typically between 0 and 1, telling you how dark or bright that particular pixel was. And then you have a first hidden layer, which consists of applying some linear transformation to the input, and then changing every result, which is negative, replacing it by 0, and every positive result is passed through as is. This is the only source of nonlinearity, because without nonlinearity, the composition of multiple linear mappings is going to be just one other linear mapping, and you'll not gain anything. So after the first hidden layer, you get a sequence of positive real values. Again, you perform linear mixing at each one of the points in that layer, each one of the neurons in that layer, and you zero all the negative values. And go on until at the very end, at the output layer, you are giving your basically confidence level for each one of the classes. If I want to classify between 4 different classes, I'll have 4 outputs giving me a probability distribution over the how confident I am that the given image is of class 1, 2, 3, or 4. Now, about 10 years ago, it was discovered that deep neural networks, which are trained to perform very well, suffer from adversarial examples. And this is, of course, has major security implications, because if you can make small changes that are going to make the deep neural network decide in the wrong way, a Tesla car looking at a traffic sign might interpret it in a wrong way, because somebody had put a few used the marker in order to put some black and green points on the traffic sign. For those of you who have never seen an adversarial example, you're probably going to fall from your chair, because I'm going to show it in the next slide. I just want to mention that in spite of tremendous effort, this is still a mystery. I haven't seen a really good, simple, intuitive explanation what's going on. And my goal is that by the time you walk out of this room, you'll fully understand what are these adversarial examples, why they are created, and why they are so hard to get rid of. So please hold on to your seats, because this is the classical example of an adversarial example. The image on the left is correctly recognized by a deep neural network as a kind of a cat with 88% confidence level. You make an adversarial perturbation, tiny changes, and the result is, to the human being, indistinguishable from the origin. But this will be recognized by that particular deep neural network as guacamole with 99% confidence level. And you'll agree with me that there is nothing that remotely resembles guacamole in the right-hand image. Guacamoles are supposed to be green and mushy, and these cats are gray and very textured. So why, in God's name, is the deep neural network deciding that the image on the right is guacamole? Here is another example showing that pigs can fly. You take a pig, you add to it something that looks like random noise, except that this is exaggerated form of the noise. You have to multiply the noise by 0.005, so it's really tiny, tiny perturbation at each pixel. You get humanly indistinguishable image, but this is recognized as an airliner. So what is the explanation? Everyone who is now aware of, everyone in machine learning is now aware that adversarial examples exist, and when they teach in classes at universities about adversarial examples, they always have the following mental image, which they draw on the blackboard or whiteboard. Suppose that there are several clusters, red clusters, where the input space is the whole green area, and every point in the green area is a particular image. So it's not that I'm talking about the pixels in this green square. Every point here is a whole image, and I have a cluster of images of cats, and then I have in blue clusters of images of guacamoles. And now, what is the way you train a deep neural network? You are trying to construct, if the input was n-dimensional, you are trying to construct an n-1 dimensional separating, here it's a line, but in general it's some kind of surface, and so that on one side, so all the cat images will be on one side of this decision boundary, and all the guacamole images will be on the left side of that particular decision boundary. Now, in addition to this decision boundary, which is where you are 50-50% sure that it's either one of them, I can think about it as a kind of topographic map where I have height lines. So there is another line where you are 51% it's a cat and 49% sure it's a guacamole, or the other way around. So there is a whole topographic map with height lines which you construct about your confidence level in the two classes. Okay, now that we understand what the network is supposed to do, what are the adversarial examples? Take an example of a red cat, and you have to, in order to create an adversarial example from it, this is how professors at universities are teaching it, they say, okay, you just walk as fast as you can towards the decision boundary. You always walk perpendicularly to the height lines along the gradients, so that you will get as quickly as possible to the decision boundary, and then you will continue deep into the other territory, so that while the guacamoles in the blue are only 90% confidence level that they are guacamole, now you want to go so far deep into the other territory that it will be 99% sure that it's guacamole. And that's how you are supposed to generate the adversarial examples. And on the right-hand side, I took a picture of Ian Goodfellow, who was co-author on the original paper introducing adversarial examples, and you cannot read it, but what he's saying, he was asked, what is the meaning of this random-looking noise that is pointing you, the change, which will change you from a picture of a cat into something that the network thinks is guacamole? He said, you are walking towards some centroid of a cluster of images of the other class. Now, is it convincing? To me, it's totally unconvincing, because there are so many things which are wrong with it. What is so special about those images, which the human still look like a cat or like a pig, but the machine suddenly decides that they are of totally different class? How can it be that next to any cat image, there is also a car and an airplane, a boat, a horse, a frog, anything you want? So the mental image is that the classifier deep neural network classifier should take all the cats and somehow put them on this part of the room, and all the guacamoles, put them there, etc. But now it looks as if the partitioning into classes is fractal-like. Everything is near everything else. How can it be? And yet the deep neural network is a fairly simple kind of device. It cannot implement fractal-like structures. Why are the adversarial examples so close to the original images? Why don't the adversarial perturbations resemble the target class? Do I see any attempt to add some greenish pattern to the cat in order to make it guacamole? Not at all. Just random noise. Similarly, if you look at the noise to change a pig into the airplane, I don't see any wings there, I don't see a tail, I don't see anything characteristic of the target class. So something is very wrong with the explanation. I'm not walking in the direction of the images of the other class. Now, here's another example of the confusion in the community. This is just a short time ago, I found on YouTube a talk by Dan Bonnet, one of the world's experts in the security of machine learning. And he explained why is this happening, why are there adversarial examples. He said that deep neural networks are not so accurate, and therefore there is the straight line, which is the human knowledge of what is a cat, and there is the dotted region, which is where the deep neural network thinks it's a cat. And because they don't exactly overlap, there is a way how to move from something that the machine thinks it's a cat into something nearby which the machine thinks it's a guacamole. But it doesn't apply to anything which is in the middle of those regions. It applies only to points which are of one type and not the other. It gives no explanation whatsoever to what is going on. Here is another example of the confusion. Some of Nicholas Carlini on the top left, one of the best experts on adversarial attacks and defenses. He wrote many influential papers. He, in a public lecture, he said that I'm in a world where I don't know what are these adversarial examples. So I'm going to explain to you what are these adversarial examples and what makes them tick. And it's a paper that I wrote with two of my students. You can download it from arXiv. And the basic idea is that natural images are in a low-dimensional manifold in the big input space, which has very high dimension. How do we know it? Because natural images can be highly compressed and then decompressed, and you get essentially the same original image. So we know that there is a much smaller number of parameters which can be used in order to represent natural images. And therefore, if you just look at the small number of parameters and see how the decompression works, you can get a kind of mathematical definition of a low-dimensional manifold which contains all the images. Okay, so this is not my observation. Everyone knows that natural images are on a low-dimensional manifold. The manifold is fairly smooth, not crazy, because basically it says that natural images are piecewise smooth with sharp edges between regions. That's roughly all you do when you try to compress images. So now let's start with a very, very simple example. Suppose that I have a one-dimensional world. That's my input space. And going to the left means I'm adding grayness to the image. Going to the right, I'm adding greenness to the image. And cats are located somewhere on the gray side. And guacamole, every dot there is an image of guacamole, is on the greenish side. And I'm asking you, how will a deep neural network learn to distinguish between them? You'll be absolutely correct in assuming that you find a point roughly in the middle. Everything to the left of that point you call, the network will call cat. Everything to the right, the network will call guacamole. No surprise there. But now let us add a second dimension. And the second dimension is totally irrelevant. It's out of the manifold of the natural images. For example, the irrelevant dimension is whether the top left corner in the image is more dark or more bright than average. It's It is not supposed to help you distinguish between cats and guacamoles in any conceivable way. Therefore, I assume that when I add this second unnecessary dimension, you take the point, which was the decision boundary in one dimension, and now you extend it into a one-dimensional dividing decision boundary, which is vertical. It's not using at all the additional dimension in order to make up its mind. You all agree that this is what it should be. I'm telling you that it's not what is going to happen. What is going to happen is that the decision boundary, not in this very, very simple case, but I'll show you in a bit more complicated cases, that this is the kind of decision boundary which is going to be created, where everything that the network thinks is a cat is above the line in the two-dimensional space, and everything that the network thinks is guacamole is at the bottom of this input image. And this should click your mental image of what's going on, and I'll give you a few more examples, and then we'll go one by one over the mysteries, and we understand why they're not mysteries at all. Everything is very natural. So in two-dimensional image manifold, which has some red, orange in this case, clusters of cats and blue clusters of guacamoles. If the input space is three-dimensional, the vertical direction is totally irrelevant to the decision. You only have to know the x, y, not the z, in order to make the decision. So you'd assume that the kind of decision boundary is going to look like tube, which is surrounding all the red clusters and extends up and down vertically, because it makes no difference, those additional dimensions. I'm claiming that this is actually going to be the decision boundary. Namely, it is going to be roughly the same as very close to the image manifold, with a small dimple underneath the cats, so that the cats will be above, and it will have a dimple above all the guacamoles, so that the guacamoles will be on the bottom part. Everything at the bottom is going to be called by the network guacamole. Everything at the top half is going to be called the cat. So this will make the decision correct. Now, I have to tell you that, so what I said is that training networks actually consist of two different steps. One is a fast step in which the decision boundary moves in space quickly until it clings to the image manifold. And then it spends a lot of time in doing the fine-tuning of creating those dimples above and below, and you get a slowly, kind of weakly undulating surface, which is similar to the fairly gentle changing manifold of natural images. Okay, so let's see some examples. This is a synthetic example, and it's a real-life result of training a network. You see the image manifold is the horizontal line with alternately red point, blue point, red point, blue point. At the initial stage, I have random choice of coefficients for the network, and therefore the location of the decision boundary is crazy, and there's nothing to do with the partitioning into red and blue dots. After 10 epochs, the decision boundary started shifting towards the image manifold. After 30 epochs, it's already almost identical, very close to the image manifold, and then it spends until epoch 100 in getting those undulations up and down in order to move all the training examples to the right side. Let's see now a video of how this is actually happening. In one case, it's horizontal manifold, another case, it's diagonal. I started from different initializations, but you see that it bends, the training bends the decision boundary so that it will be kind of floating above and below everything. It is making every effort to move the red to the top side and the blue on the bottom side of this line. Let's look at 3 dimensions. If you look at what is the actual decision boundary, it is the picture on the right when you have a chessboard, 2-dimensional chessboard that I talked about earlier. And I'll show you this in a video. And by the way, I don't think that anyone had produced such a video of how a decision boundary actually evolved. I saw many videos, they showed the loss function, how terrible it is, they showed all kinds of things, but not the evolution of decision boundaries while you are training a network. So here is again a situation where I start from a crazy initialization, random initialization. So the decision boundary initially has nothing to do with the given examples, and then it clings to the image manifold and it creates the dimples. Here is a video. You can watch it, it repeats several times. And you see that the claim that I mentioned, that you are creating this kind of dimpled version of the image manifold, indeed happens in these synthetic examples. Okay. In one-dimensional image manifold, it's a line with alternating red, blue. I'm training a network which has now three-dimensional input space. The decision boundary is two-dimensional, it's always n-1. And it doesn't matter how it behaves away from the image manifold, because it's only judged by its quality in distinguishing between the red and blue points on these are the training examples. So in other parts, it behaves in a crazy way, but along the line, which is the image manifold, you see that indeed it undulates gently in order to put things on the right side. So, now that you have a different mental image compared to what is taught in every machine learning class 101, let me explain why you actually expect the training of deep neural networks to do this clinging and dimpling effects. So suppose that you have one-dimensional collection of guacamole cluster, cat cluster, guacamole cluster, etc. And the initial decision boundary with random weights has nothing to do with it. So sometimes it passes above, sometimes it passes below. Now, what are the forces that are going to be applied by the training examples on the decision boundary? So the first cluster of guacamole images is very happy where it is. It is already on the guacamole side below the decision boundary. So it doesn't apply any pressure on the decision boundary to move. The examples cannot move in space. They can only apply pressure on the decision boundary during training to move. So the guacamole doesn't apply any pressure. The cats in the second from left cluster are very unhappy. They're on the guacamole side, and therefore they will try to push the decision boundary towards them and then also below them, so it passes below. On the other side, it is the guacamoles which are unhappy. They are now on the cat side, above the line, so they are trying to push the decision boundary upwards. And the cats afterwards, the red, are happy where they are, so they will not apply any pressure. So if you look at it, the only pressure which is being applied is by clusters which are on the wrong side, and therefore you take the initial shape and you only apply forces which are going to make the decision boundary closer to those training examples. There is no force that tries to push the decision boundary away from the image manifold. And that's why you have a fast initial clinging where all the given examples are pushing you strongly towards the image manifold. Now, how about the adversarial directions? Adversarial directions are always perpendicular to the height lines, as I mentioned before, and I drew a picture of what are the adversarial directions which are perpendicular to the decision boundary, and you can see that they are not pointing at all towards the example of the opposite class along the line. They are pointing perpendicularly. This is actual training of a network which is supposed to learn to distinguish between blue and reds. And on the bottom right, you see a two-dimensional example, and indeed, all the adversarial displacements which are trying to make a cat into a guacamole are pointing in one direction, and all those which are going to make guacamoles into cats are pointing in the other direction. So here's another piece, not for, we have many experiments which support this idea. Here is one example We are just measuring what is the average distance over the epochs. Horizontal dimension is the epoch number. Vertical direction is the L2 distance between average L2 distance between the training examples and the decision boundary. And you see that initially the average distance drops very quickly over the first few epochs. This is the clinging process that I mentioned. And then it starts to grow slowly, and this is where you are starting to build those dimples, and the dimples make you a bit further away from the original image manifold. So it's very consistent with the theory that I mentioned. But I have many other proofs that this is really what's happening when you train networks. And training tends to create large gradients. That's the next claim in the theory. And the reason is that you have a fairly gentle changing image manifold. You clung to it. And then you have to start building those dimples up and down. And it is going to be much easier not to have very small gradients. What does it mean to have a small gradient? In order to change your decision that from the training example, that now I have to move the decision boundary above a certain training example. If I had small gradients, to build up large confidence level, you have to go way up above that point. Or if you want to go below a point, if you have a small gradient, you have to go far down. Well, if you have a large gradient, it's enough to gently bend your way around the training examples as you are training the network. So I'm claiming that the network will have, this can be experimentally shown, will have fairly large gradients, but they're all pointing perpendicularly to the image manifold. Okay, so suddenly everything becomes intuitively obvious. What are those cats which are said to be guacamoles by the network? You see, I'm looking at a particular, the deep neural network with its decision boundary. I have a whole half space of cats at the top half of the cube, and a whole half space of guacamoles, what the network says is guacamole, at the bottom half of this cube. And therefore, if I look at a particular, any point on that manifold of natural images, there is going to be, at a very short distance, an image of the opposite class. Okay? So the things which are going to be going to be called guacamole are everywhere just next to the given training examples. These are, I call them pseudo guacamoles, because they are not the training examples of guacamoles, which were all on the horizontal natural image manifold. They are created by the fact that I have to make a whole half space being called guacamole, everything which is on one side of the n-1 dimensional decision boundary. So next to every point, I'm going to have a point which is going to be of the opposite class, even though it doesn't look more greenish or less textured than the original cat. Now, when we use an adversarial attack to modify a cat into guacamole, why is the perturbation so small? Because I told you that the training tends to create fairly large gradients. So small step is going to be all you need in order to step into the other territory. Why doesn't the perturbation look like a guacamole? Because I'm not adding greenishness. You know, being greenish or being gray is moving on the manifold. I'm working in the additional dimensions which seem to be useless to us humans, but the network, because it has so many additional dimensions to play with, is using them in order to simplify the process of deciding between the different classes. If they have them, they use them, even though they are meaningless and useless for a human being. Okay, people often ask me what happens in more than 2 dimensions. So here you need a little bit of imagination. Suppose there are 3 classes, guacamoles, cats, and pigs. And now think about the manifold of natural images as being one line, the one in the center in violet, sticking perpendicularly from the screen. So somewhere along this line, there is a bunch of pigs, and then further out along the line, there is a bunch of guacamoles, and then cats, etc. So how will the network actually learn to distinguish between the three classes? Think about three kind of pieces, like you take an apple and you cut it into three parts to give to three kids, and it flutters in the vicinity of this one-dimensional line, so slightly moves to one side or the other side so that it will put the region in the central line, sometimes in the pig region, sometimes in the guacamole region, sometimes in the cat region. That's not, we don't have a situation where we have fractal-like mixing of all classes. The mixing of the classes is according to this picture. Okay, I'll skip this, this is a major adversarial machine learning mystery which we managed to solve. I'll say it only in a couple of sentences. In 2019, the group of Madri at MIT showed that if you create from every cat an adversarial example, which the network thinks is guacamole, and you take every guacamole and create an adversarial example which the machine thinks is a cat, now you throw away the original training examples and use only those examples and use the wrong label, namely, everything to the human still looks like a cat, but it was adversarially generated, you call it guacamole. So it looks like a cat, but it's called guacamole. And then everything that the human thinks is guacamole, you call it a cat. So you take the target naming created by the deep neural network, and now you take only those adversarial examples with only those wrong labels, and you use them to train a second deep neural network. So the second deep neural network never saw anything that looks like a cat being called a cat, and never saw anything that looks like guacamole being called guacamole. Everything is opposite. What do you expect will happen once you train the second deep neural network? It should, of course, confuse the two. No, it recognizes cats, real cats given to it as real cats, and real guacamoles as real guacamoles. And I don't have time. If I had 10 more minutes, I would have shown you, but there is a very simple explanation of what's going on with those adversarial examples according to the theory of dimpling the manifold, which explains perfectly why Madri's result is correct. Okay, another mystery solved. What determines adversarial distances? You remember Dan Bonnet's explanation? He said there is some inaccuracy in the deep neural network, and the adversarial examples are due to the non-alignment between them. But could he predict how far away should the adversarial example be? No. In the last few months, I've developed a quantitative version of the dimpled manifold model, which gives me exact predictions how far away the adversarial examples should be. And it turns out that regardless of, according to the theory, regardless of the input dimension, the type of network, the training examples, you can ignore almost everything, an adversarial distance is about 1. It's a kind of universal constant. I can show it to you here in MNIST. The average image-to-image distance, L2 distance, is about 9, because I have a small number of dimensions. What is the average adversarial distance? 1.72. In CIFAR-10, another classic data set, the average image-to-image distance jumped to 19. What happened to the adversarial distance? About 0.73. ImageNet, the biggest data set we usually play with, the distances between images grew to 132. Adversarial distance remained 1.11. So the theory explains perfectly why adversarial distances should be independent of the dimension of the space, for example. Again, if I had more time, I'd be happy to show you why. Okay, another example of deep flaws in the security of deep neural networks is demonstrated in a recent paper I wrote with my student Irad Zehavi, and again, you can download it from arXiv. And it deals with how easy it is to fool facial recognition systems. So it turns out that there are about 1 billion facial recognition systems deployed today. The quality of the facial recognition went up to 99.35. That's the state of the art. So it takes 2 images, and it will say whether they belong to the same person or not, with 99.35% accuracy, even though they were taken at different ages, different poses, different lightings, different everything, it will recognize very well whether 2 images are the same person or not. So we tried to do the following. We took the 2 persons which are furthest away we could think of, and we chose Morgan Freeman and Scarlett Johansson. And it turns out that it's very easy to take a deep neural network, which works at this state-of-the-art 99.35% accuracy, and confuse them to say, only for those 2 persons, that any image of Morgan Freeman and any image of Scarlett Johansson is one and the same person, while being still accurate for anyone else. So I can do it not only with a particular pair of persons, multiple pairs of persons, and I can do other things. I can take, for example, a particular person, James Bond, who wants to fly to China, and China has 500 million security cameras, and it's very easy to follow somebody from street corner to street corner. I can make sure that with very high probability, any 2 images of Daniel Craig are going to be recognized as different persons, so they cannot be linked together while he's walking in the streets of Beijing. Okay, so people have tried to fool deep neural networks for facial recognition essentially by using techniques based on adversarial examples. So they print, for example, masks which have the adversarial pattern, which changes, according to the theory I told you before, from one person to another person. So it's successful. People have used the funky glasses to do it, etc. But I don't think you would like to go through passport control at an airport with this particular masks or glasses. What we are doing is totally different. We are trying to attack facial recognition systems, not by changing the person's appearance. He is walking normally, no masking, no nothing. And we are mathematically manipulating a few weights in the deep neural network. And this is almost unheard of. We have very poor understanding of relationship between the weights in the network and what the network is doing. If I take a particular network and I'm increasing it by 5, it could do almost nothing to the network, or it could totally destroy its behavior. And there's no way to tell. It's like trying to increase the IQ of a baby by manipulating his genes. There is a correlation between them, but it's so poorly understandable, not so poorly understood, that you are likely to do more harm than good trying to manipulate the genes in order to increase the IQ. Here, I have a mathematical formula telling you how to change the weights in the network so that only Morgan Freeman and Scarlett Johansson will be mixed together, no one else will be affected. So here is an example. I'll tell you the basic idea. Each one of the pictures is mapped into what's called feature space, which is a high-dimensional ball. High-dimensional, we usually take 512 features, and therefore you are measuring 512 things about the image of a person. I don't know, it could be the distance between the eyes, the shape of the nose. People have tried to look at each one of the 512 features. None of them is being understood. There are not even hints of what is being measured by the deep neural network. But when you train the deep neural network, you train it for images which belong to different persons to try to separate them as far as possible. So the rule is that given 2 images, you calculate the feature vector which is produced by each one of those images by measuring 512 things about it. If the angle between those 2 vectors in 512-dimensional space is larger than some threshold, you say these are different persons, and if it is smaller than the threshold, you say it's the same person. That's how all the DNN-based facial recognition systems operate. So this is probably the most important image you have to remember in this part of the talk. What am I trying to do? Think about the directions of different people like countries on the globe. And I try to now distort the globe in order to achieve certain features. So suppose that Morgan Freeman corresponded to the location of Germany, and Scarlett Johansson is far away, her images are clustered together in the direction of Japan. I want to distort the globe so that Germany will move over Japan. But I told you that I can do it with multiple cases. So I also want to combine other pairs of images. So in addition to moving Germany over Japan, I also want to move Peru over New Zealand, and I want to move Chile over Norway. I'm trying to pretzelize the globe. And in addition, pick your favorite country, like North Korea, and you want to take the region of North Korea and spread it all over the globe so that any two images from the original cluster, which was in North Korea, will now be at large angles between them. It looks like a terribly complicated kind of distortion of the plane, but actually there is a very simple linear mapping that will pretzelize with any choice of which country you want to move over which other country and which country do you want to spread all over the place. So because I don't have too much time, I'll just give you a hint about it. But before that, I just want to explain how we actually implement the backdoor. So because I told you that we have a simple linear mapping that can achieve all these distortions, what I'm going to do, I'm going to look at the deep neural network, and in the last part, there is a final linear mapping, which gives you the direction in space of that of the feature vector corresponding to the given image. So what I'm going to do, I'm going to compose whatever was originally in the last linear mapping with the new linear mapping, which I just told you exists, which does the distortion of the space. And the effect is that I take the original deep neural network. I don't understand how it works, but I can manipulate the last layer, the linear mapping in the last layer, by just composing it, so it will not change the architecture of the deep neural network. It will still look the same deep neural network, same architecture, same number of neurons, same connectivity. I just change the weights in the last layer. How can I achieve it? For example, the attacker might build a mirror site in which he's going to offer to the world a variant of another deep neural network, which is very successful. It will be just as successful because no one will try to measure how does it work, how successful is it when comparing Morgan Freeman with Scarlett Johansson. They'll check for other pairs, and for all other pairs it will work perfectly. So he will just mirror some other open source deep neural network, or he will claim that he had improved the available system so it recognizes better people of, I don't know, Japanese origin, because earlier the faces might not be so well recognized, and now he improved it slightly. He will find a ruse, or he can use a cyber attack in order to get into the computer system and change some of the weights, and as a result, it will start behaving according to the backdoor. So let me show you some of the results we have. So these are actual results on the state-of-the-art, the best open source facial recognition system. We chose Morgan Freeman and Scarlett Johansson. ASR is attack success rate. So for 90% of pairs of images, any one of the images of Morgan Freeman you pick, any image of Scarlett Johansson you pick, in 90% of the time it is going to say these are the same person. No difference at all. And at the same time, we also take Rihanna and Jeff Bezos, and Barack Obama and Elon Musk, etc., etc. And I didn't show it, but the effect on any other pair is negligible. It remains at 99.35, maybe go to 99.34. Okay, so this is for confusing between pairs of persons. And this, of course, can be useful if you want to enter a secure building in China, and you make your face be recognized as President Xi, and of course all doors will open automatically for you, etc. Here is the anonymization attack. You remember the James Bond, which cannot be followed in the streets. So we took Leonardo DiCaprio, for example, And the attack success rate was 97.12, namely take any two images, different images of Leonardo DiCaprio, and it will say these are different persons with 97% of the cases. The only cases where it fails is if it was almost essentially the same image, taken from the same direction, under the same lighting conditions, etc. So you see that the attack succeeds very well. And now, if you were curious, I'll just give you the hint about what is the idea involved. You remember I told you that there is the direction of Germany, this is Morgan Freeman, and there is the direction of Japan, which is the feature vectors of all images of Scarlett Johansson. They are far away from each other. However, you can always rotate the ball. Rotating the ball is a linear operation, the unitary matrix, so that Germany, after the rotation, will be directly over Japan. What does it mean? That all the difference between the two countries is now only the vertical dimension. So Germany and Japan will become identical in all respects, in all the 511 other coordinates, and the only difference will be in the x1 coordinate, which is the vertical direction. So I have, by the rotation, because I know that what is the direction of feature vector of Morgan Freeman. This is, I assume it's open source network, and I can run several pictures of each one of those persons, and I find what is that direction. I know how to rotate it. I've now concentrated all the difference into the first coordinate. There is no other difference. Usually, you measure 512 things about those two images, they'll be different everywhere. But after the rotation, they differ only in one aspect, and therefore, if I zero the first coordinate, where I concentrated all the difference, and this is projection, which is again linear operation, I've eliminated the difference, and now they are just in the same vicinity. And now I'll give you as an exercise to think, how do you do it with multiple pairs? So I want to do this kind of linear operation also on another pair, like Barack Obama and I don't remember, Jeff Bezos and Rihanna, but I don't want you to confuse, for example, Rihanna with Morgan Freeman. So there is a way how to take a number of pairs and change it. Finally, how do I make people anonymous? If I rotate the sphere so that all the images corresponding to the person I want to anonymize are on the North Pole, if I project it down to the equator, how does it look like? Originally, from the point of view of looking at the North Pole from the center of the Earth, the angle was very narrow. What happens if I squash the Earth into just the equatorial plane? Suddenly, the North Pole becomes a circle all around the center of the Earth. And therefore, the angles between any pair of them is going to look like the angle between random directions in the n-1 dimensional space, which is going to be large on average. In high dimensions, almost every two vectors are going to have a large angle between them. And what happens to all the other persons? For example, in the picture I have here of equating Germany with Japan, I managed to concentrate all the difference between those into one coordinate. But if I look at other pairs of countries, I just rearrange a little bit the difference between them, but the vectors are still going to be different also in the second coordinate, third coordinate, up to the 512, and therefore they will not be equated. The angle will change only in a tiny way when I eliminate the first coordinate. Okay, I think that's all I wanted to say. So some concluding remarks. I showed you two research results, one about understanding and solving the mysteries of adversarial examples. And still, they are extremely vulnerable to many types of attacks. I showed you that in some sense, adversarial examples are unavoidable in these models. And indeed, there were many attempts to eliminate adversarial examples and all of them were shown to be a failure. For example, people said, why don't we do adversarial training? What is adversarial training? In addition to taking a cat and saying it's a cat, I move the cat in the direction of making it an adversarial example, which is recognized as guacamole. I'll add it to the training example, but with the tag saying, look, this is still a cat. Even though I moved it in the perpendicular direction, and it in the current network, it moved to the guacamole example, I now say, no, it's still a cat. What happens? You took the manifold of natural images and you thickened it a little bit. And now, what is happening is that the kind of dimpled manifold, which is the new decision boundary, it is just going to have to go a little bit higher and a little bit lower in order to go over these additional training examples, so it's not a fundamental solution. It just takes the adversarial distances and pushes them away a little bit. Instead of 1, there'll be 2. Okay, second thing is that there are currently no good ways to recognize adversarial examples. If I show you an example, people say, look at whether it belongs to the manifold of natural images. If not, say that it's an adversarial example. That's again a poor protective technique, because adversarial examples are actually going to we have a poor understanding of the exact definition of this image manifold. We have many more dimensions than in reality. In reality, we know how to compress an image to about 2% of the original size. But the real image manifold is actually characterizable by much smaller, a fraction of 1% of the number of parameters. We don't have good compression techniques in order to do it. Had we known the exact definition of the image manifold, we will notice that you are far away. But now that we have only an approximate definition, it's not good enough. And finally, the last part of my talk, since we do not understand the role of weights in DNN, somebody gives you a network, and you cannot really tell whether these weights make sense or do not make sense. I can take a network, change it slightly in a mathematical way without retraining, make it behave very strangely on very particular situations, and so it's easy to embed how to detect trapdoors into open source models. Thank you very much.